We are thrilled today to be welcoming Dr. Necip Berme. He's the president and founder of Bertec Corporation. And his talk is going to be on biomechanics from the lab to the clinic, a brief historical perspective. So it's a refreshingly personal account of the history of biomechanics and how he and others in the field and their work may be affecting what you do in the clinic today. So super interesting and personal and fun. So Dr. Berme is a professor emeritus in the Department of Mechanical and Aerospace Engineering, The Ohio State University, and founder and president of Bertec Corporation. His background is in mechanical engineering and applied mechanics. He taught mechanical engineering in Turkey, where he was born and raised. Subsequently, he taught biomechanical engineering in Scotland, where he was the head of the rehab group in the bioengineering unit, University of Strathclyde. Later, he moved to Columbus, Ohio, where he taught mechanical engineering and biomechanics until his retirement in 2008. But he clearly wasn't fully retired. So he founded Bertec Corporation in 1987, where he currently serves as the president. During his academic career, he co-edited 2 books on biomechanics. He also authored or co-authored over 100 articles. And later, during his tenure at Bertec, he helped to develop new technologies and has over 60 US patents awarded to him. So welcome. We're so excited for your talk. And then, of course, Fernando Santos. Dr. Santos has his Ph.D. in biomechanics and movement sciences and is an accomplished PT who worked with Paralympic athletes and people with balance impairments in his own clinic. He's a senior applied biomechanist with Bertec and also my partner in creating this webinar series. So you'll recognize him if you've been here before. So my name is Alyssa Heine. I work in knowledge management and learning and development at Bertec. And I am going to go ahead and share my screen in a second. But just a reminder, if you have any questions at all during the pre-recording, feel free to add them to the chat, and Dr. Berme and Dr. Santos, anyone can answer those for you in the chat. And we'll also reserve time for a Q&A afterward. So in the meantime, enjoy, and I'm going to go ahead and share my screen.
Hello. The idea with this talk is to see how research done in the lab has translated or not translated any clinical practices. It's a huge area. So I am going to limit this, my personal experiences, my personal involvement in biomechanics, and to do my direct and indirect experiences with this. But how far back I'm going to go, I'll start with a phone conversation I had a few years back. And somebody called me asking about force plates. And during the conversation, I found out that this person had studied at the university where I used to teach in Scotland. So I asked him who his advisor was, and he gave me a name, and which I did not recognize at the time. And I asked if he knew Sandy Nicol. Sandy was my doctoral student that we will come back to eventually later on this talk. And so this man said, oh, Professor Nicol was my advisor's advisor. Good grief, I said, that puts me 4 generations academically senior to this man. Okay, so let's go on and look at things here. Now, biomechanics was not my first love. In the 60s, I was more involved in stress analysis, experimental mechanics, and this particular slide goes to the 60s when I was at Case, and I keep calling it Case because Western Reserve was a separate university at the time. I was interested in the stresses in pipe cutters of all things, and I built my own load transducer and other displacement transducers to understand what the loads are experienced by the cutter during this process. So just to put a perspective, historical perspective, this is when the Watts riots were taking place. Kent shooting, Kent University shootings took place. I attended a few of the Martin Luther King rallies. not sure whether it was a good thing or a bad thing. I never went to Woodstock. So having said that, so this puts a sort of historical perspective to that timeline. So my first involvement in biomechanics, when I went back to Turkey, met an orthopedic surgeon who was interested in forces transmitted between the bones using an external fixator. So I instrumented an external fixator, and we had a dog model that we worked on. This project really didn't go very far, but it sort of introduced me to biomechanics, and I ended up designing my first force plate in 1970. So in 1974, I moved to Scotland, where I became part of a biomechanical or biomedical engineering department. And now, just to relate the research I have done there, let's just go back perhaps 15 years or more so back. And really, the biomechanics as we know it started after the Second World War, when there were lots of amputees and prostheses were not fitting well, and veterans were not walking comfortably with the existing prostheses. So this slide, unfortunately, I don't have a reference for it, but I believe it's from UC California, UC Berkeley, and New York University joint report on this project. The subject on the left has pins attached to his bone, literally drilled and put there, so that they can monitor the small movements of the bones relative to one another. The subject was a prisoner, and I'm not sure, nobody really volunteered the information how the prisoners got involved being test subjects. Obviously, ethics have changed since then, and although in the 70s or the 80s, people experimented on themselves, researchers. I have known a researcher who attached a force transducer to his Achilles tendon, another researcher who actually did surgery on himself and attached strain gauges to his one of his bones. But just going back to what had happened in the 60s, in order to do these biomechanical research, they used 3 cameras, synchronized cameras, that would be filming the subject. They had designed the first force plate. That first force plate design was published in 1952 by Cunningham and Brown. I had an opportunity to meet with Cunningham in the early 70s and had a chance to compare his design with my design. So that was an interesting meeting. So the difficulty, if you can realize, you have to analyze the film frame by frame. Now, just stepping forward to my own lab, where we had synchronized cameras, and perhaps you can see a couple of force plates in the floor. We used, let's say, 10 markers on the body that the cameras would see as bright spots, and at 50 frames per second, you can calculate the math that you have so many markers to digitize in order to collect even 1 second worth of biomechanical data. So one of my colleagues thought that it would be wise to be able to automate this system. And in order to do that, they started looking at bright spots on the person and a video camera, which they clocked each line of the video image to 1,000 points. They counted the frames, they counted the number of lines so that they can get the, the bright spots, location of the bright spots in the video image. So two students, Brian Andrews, marked in red, and Mick Jarrett, here you don't see his face, were really instrumental getting this project going. Sheila was the computer operator here, state-of-the-art PDP 11, which probably is less powerful than a cell phone today. So they came up with an automated system that would record the bright spots. The university, in their own wisdom, sold this technology to Oxford Medical. Oxford Medical really did not want to get involved in developing this system. So Julian Morris and a few other people from Oxford Medical separated and formed a new company called Oxford Metrics. This was probably a joke, but Julian had told me that they chose the name of the company because Oxford Metrics and Oxford Medical had the same initials, and they could really use the stationery they had already had with OM printed on it. So, however, so if we move on to the various projects I was involved in, and the modular prostheses were just coming in, the artificial limbs. And modular meaning that you have a shank unit, you have a foot, and you manufacture a socket and try to put these two together and align them for the patient who is going to wear. So there were many things that were unknown. There was no objective data on the alignment requirements, alignment ranges. There was no real information feedback from the patients. So, so that was a 3-4 year project I was involved in, and my colleague Stefan Solomonitis was the lead investigator in that, and I hear that Stefan is still active in biomechanical research in Scotland. So part of this project was obtaining what sort of design requirements as far as loads are concerned for these prostheses. And they had a pylon transducer, 6-component transducer, but that did not really fit in most of the prostheses because this pylon design was far too long. So I designed this much shorter pylon transducer, which was published in 1975. And we used that design to find what sort of loads a prosthesis should be able to withstand. Because without that knowledge, parts of the prostheses were failing and components were cracking or falling off. So that was that project, and definitely the lab research that we have done helped with the clinical product that was eventually developed. Similarly, at that time, plastic orthoses were coming in, and I was particularly interested in the ankle-foot orthoses. And one of the things that I did was that I attended a weekly clinic seeing patients with the orthotist and the physician who would be prescribing the orthoses. And this is funny in a way that the patients usually came to the clinic wearing their best clothes and best shoes, and we would really wanted them to put on their most worn out shoes so that we can look at the bottom, the sole of the shoe, and figure out how they walk and what parts of the shoe is worn, etc. So that sort of was a challenge to get them use their oldest shoes, worn out shoes to come to the clinic. But just going back to the biomechanics, after fitting the orthoses, we looked at gait analysis with these patients and looking at the flexion extension or plantar flexion, dorsiflexion moments at the ankle joint and comparing it with the normal population, which is represented by the shaded line here. The ankle foot orthoses and without ankle foot orthosis really did not make a huge difference in this particular patient. But this patient had exceptionally high knee moments. And looking at now flexion extension moments for the knee and comparing this with the normal population, without the ankle foot orthoses, you can see that the red line is probably twice as high of an extension moment, and the knee was hyperextending. And the prescribed extension actually minimized the hyperextension, but again, shown here as the extension moment in the yellow line is still the hyperextension or high moments existed at the knee of this patient. So we tried to put some built-in dorsiflexion, another 5 degrees, for example, which brought down the hyperextension moment to within the normal range. So this would have been a good way of prescribing prostheses by actually collecting quantitative data, but the gait analysis took such a long time, and this was not a practical thing to do for the patients at the time being. Now, moving on to joint replacements, probably John Charlie was the first surgeon who did first full joint replacement of the hip using bone cement. He had an acetabular component which fit in there and a stainless steel part which fitted into the femur. Now, I did not know Charlie well. I met him a few times and talked to him and asked him questions, but I knew his engineer. So the engineer was explaining to me that they wanted to obtain force data for the hip replacement. What are the forces transmitted at the hip joint? Because the previous replacement, people have even historically tried glass cups or Pyrex, which failed drastically. So I think Pyrex sort of survived. But so they wanted to find out what sort of forces this joint needs to be designed for. So they decided to look at the single-legged stance. And here in this diagram, you're looking at an imaginary cut through the hip joint. On the top sketch here, the blue line is the body weight. The green line is the muscle force that would balance the body weight about the hip joint. And the resultant force, probably 2.5 times the body weight, was transmitted through the joint itself. So one of my colleagues had extended this kind of study and started looking at, this is going back before my time, looking at walking and running, and came up with in walking the ground reaction for, or the hip joint force can be as high as 3 to 4 times the body weight because of the involvement of extensors and flexors. And in running, it can go as high as 7 times body weight. So, okay, good. They knew the forces, but in the first replacement joints, they did not really consider the material properties, that they used a Teflon cup to minimize the friction. And Teflon has terrible wear properties. And Charlie was telling me that after the first couple of years, he had to go back and revise these surgeries, operations, and replace the Teflon cups with high-density polyethylene cups. Another interesting point here is that the head of the femoral head of the prosthesis was 22 millimeters, and I thought that was really an interesting dimension. How did they choose 22 millimeters? And the answer was curious, interesting, because they said that they only had 1-inch diameter stainless steel rods available to them. So they had to fit everything into that size of the head. So that's why they had 22 millimeter cups. Now, I was involved looking into the bone resorption due to the loads transmitted through the prosthesis to the bone, and developed simple models looking at parametric models, looking at what modes of load transmission can exist. At the time, there were lots of people getting involved in this, and finite element models were starting to be used in analyzing the interface between the prosthesis and the bone. And this sort of lab work certainly did help to develop better prostheses, and can be considered as a success as far as the laboratory or experiment, the theoretical or computer type of work being transferred to a device which is widely used in the clinic. Now, one of the things that were not known, and unfortunately, they thought they knew what they were doing in the 70s, but not knowing what that you're not knowing something is a terrible thing. Most people thought that hinge joints like the elbow and the knee could be replaced by pure hinge prostheses. But these prostheses started failing rapidly. And here in this X-ray, probably on the right bottom side, you can see that the prostheses were sort of protruding through the bone, and the bone here is resorbed. And if you sort of look at another patient, here it's another catastrophic failure. So these prostheses, hinge prostheses, were a terrible failure. And so we decided to start looking at the design requirements for prostheses, the motion between the bones, and what sort of loads the prostheses should be able to transmit. And Sandy Nickel, that I mentioned earlier on, was the doctoral student who was responsible for carrying out this research. So we decided to measure the forces between, in normal daily activities, between the subject and the ground, so to speak, here. And these are the markers. These are still using movies and digitally, sort of manually digitized markers. And then using this information, we calculated the resultant force and moment transmitted at the elbow joint. And using that information, we developed models to predict what the actual joint loads and the muscle loads would be. In a mechanical design, you would have 6 unknowns and 6 equations typically that you can, equilibrium equations that you can solve. If you have more unknowns, you rely on the stress-strain relationship and deformation of the materials. However, this obviously cannot be done for human subjects or by animal subjects. So we had to come up with some assumptions. For example, in this case, we assumed that the force transmitted by each muscle is proportional to the bulk of the muscle, and then used EMG to sort of verify that this was happening. We also used an iterative method of modeling how the forces may be transmitted through the joint and looking at one of the planes of the load transmission here for in this case, the right elbow. And we assume that if the external load is more central, then the load is transmitted equally within the joint. If the load has an offset, meaning that there is an external moment, then one of the condyles would be loaded more, and higher the moment that the joint load shifting in this direction. And then we looked at parametrically what else can happen, the ligament force, a joint force, and a joint force in the distributed between the left and right side, or the medial and lateral sides, and the ligament force here. And with that knowledge, we were able to have bench tests for the designed prosthesis. And also after the bench test, we were able to carry out some cadaver tests. And then we were able to finalize the design, which more or less mimicked the anatomical joint itself, with then two components. Again, I believe this was stainless steel component, and then again a high density polyethylene component. And this was very successful. This design was used by a subsidiary of Pfizer and probably was on the market some 25, 30 years. So that I would put in to have a success column of the rigorous lab work resulting in a successful medical device. Now, we were then recruited to look at the metacarpal phalangeal joint. We used the same process of calculating the forces transmitted at the MCP joint. And in order to do that, we used a simulated tap with 6 component force transducers measuring the forces between the fingers and the tap. And also in this particular case, we had a clutch that would restrict the rotation, so you can change the resistance of turning the tap. And we use similar setups for, say, opening and closing a jar, how the hands would be really engaged with the environment, so to speak. We did lots of dissections to look at the line of actions of the muscles, ligaments, and we developed a tiny marker system, again, using the movie cameras, how the bones moved relative to one another. Now, unfortunately, the money dried up. The company that was sponsoring realized that with a new design, however good it may be, they cannot compete with the Swanson joint, which was a silastic joint for the MCP joint at the time, and they decided to drop this project. So unfortunately, we had lots of design data, finger forces information, but this project really did not translate into any clinical practice because of the economics of the situation. So now moving to my tenure at the Ohio State University, and I'm sure you'd be wondering what on earth a device like this, a walking machine, has to do with biomechanics. This was a gigantic walking machine that I was involved in the design and development of it. But my main involvement really was in the area of biomechanics, because this device needed to negotiate obstacles and be able to walk and go over terrain, etc. So we thought that a goat model would be a good one to study. So I built a force plate to monitor the forces between a jumping and a running goat and the ground. And we did experiments with goats, trying to understand how these animals negotiated obstacles. As a result of this, the student who was involved, Marcus Pandy, and I understand he is now a professor of biomechanics in Australia, started looking at mathematical modeling of walking and how to predict or algorithms for making models walk. And at that time, I realized that we really don't know enough about balance. So I started getting interested in balance and started working on balance. Now, this, my interest in balance eventually turned into a clinical product. Lou Naschner in the 60s and 70s was the person who developed the computerized dynamic postragraphy, where the surround around the patient and the ground on which the patient was standing were perturbed, and the balance parameters relating the patient were looked at. So with the collaboration of Lou Naschner, we looked into the options of using virtual reality and immersive system for a similar test or the same kind of computerized dynamic postragraphy. And we came up with a device that is really, for the last 3, 4, 5 years, have been clinically accepted and well used in assessment of patients with balance disorders. So I would put my involvement in balance and collaboration with Lou Naschner as a clinical success. So this brings me to the end of my talk. I know that I skipped a lot of things, and but this is the end, and I would be happy to answer any questions you might have. Thank you.
Hi there, welcome back. Thank you, Dr. Berme. That was refreshing glimpse into the history of biomechanics, and certainly those images were
it is interesting to listen oneself. I did not realize that I cleared my throat so often, but
that's what we're here. This is an intervention. That's what we're here to talk to you about. Thank you for preparing that for us. I think that was refreshing and interesting for everyone. So I'll kick it over to Fernando, Dr. Santos, for the Q&A portion, and I'll turn off my camera.
Hi, hello everyone. Hello, Dr. Berme. I talk to Dr. Berme at least once a week, right? So, and he always have really interesting stories about his trajectory in biomechanics and on this tech world of healthcare and technology. So I have a couple of questions for you, but I also like to tell everyone, feel free to put any comments or any questions on our chat right here. And let me just kick off with a couple of questions. So how did you came up with Bertec? How everything started at Bertec? It's almost like a personal question.
It is, and I call Bertec perhaps an accidental company. When I moved to Ohio State, I knew that I had to get grant money to support my graduate students. I had an NSF grant and then NIH grant, and I had something around 10, 12 grad students at any given time. And alongside some of my colleagues in other countries wanted me to build transducers for them, and I did that as a hobby. But I really didn't enjoy writing grant proposals, and that was the only way to find money for the students. So I had this brilliant idea that I can build force plates and sell them to biomechanics researchers, and I can use the money to support the students. So that's how the whole thing started. And for quite a number of years, almost up until my retirement from Ohio State, Bertec was perhaps a 3-4 person company, one technician, couple of grad students, and sometimes myself, sometimes my daughter helped out with it. And then after I retired, or around that time, my son showed an interest, and perhaps I twisted his arm to leave Microsoft and come to Bertec to be involved in this business and help the company to grow. And that's how Bertec became what it is today.
Very nice, very nice. So we have one question there, but from Charlie. Charlie, I'll come back to your question in a moment, because I want to know, Dr. Berme, what is some of the most unusual uses of force plate technologies that you've ever seen over the years?
There were many uses and misuses, but probably the most interesting would be this is going back years. Canadian Space Agency bought 2 custom force plates from us, and they used these force plates to test the robotic arm of the International Space Station before it was launched. And on one of the force plates, they mounted the robot arm itself, and on the other force plate, they were putting payloads or small objects, and basically they were testing the control software for this. For obvious reasons, they had to make sure that the robot arm would not go and smash something. So that probably is a very unusual application of a force plate.
And a pretty cool one. So Charlie, question is, where do you see the technology going from here? And I will twist this a little bit, not just where you see it, but where do you want to see this technology go in the future?
I think although things have developed over the years, it still takes a long time to analyze data. Force plates are still expensive. I really would like to, and we work on this all the time, reduce the cost of force plates, and so that in fact we can have an instrumented floor, and that we can have almost a gait analysis type of assessment of the subjects as they walk into the clinic, for example. Obviously, that has to accompany with knowing exactly what we are looking for, etc. It's a long road. I don't know if this is going to happen in my lifetime. But in the sports area, we see force plates being used in jump analysis, in golf analysis. So there is hope that something is going to happen eventually.
That's great. Does anyone have any more questions? No more questions?
Well,
No?
let me acknowledge, in fact, I see
yeah.
Susan Dorn here, and Susan was the person who introduced Lou Naschner to us. So thank you, Susan.
It's a big one.
Nice.
Yeah, let's thank her.
That's nice. That's nice.
That's great. Okay, so, oh, I see another question just showed up. So why don't we take that one before I jump in?
Mary, I don't know if it's a question, just let me read this. Great historical perspective. Dr. Berme must realize that this numerous publications and inventions have been used by many biomechanists and device designers to help design and understand human movement and improved device designs. I have used data that he and his students and many others have generated. This is Thurman from Biomech. Nice, really nice.
That's great. Well, don't hesitate to add any more questions as we wrap it up here, but I will go ahead and plug the ones that are coming up so you can put them on your calendar. And you can actually go to the Bertec website and you can see a calendar of upcoming topics and register for them right there if you're not on our mailing list. And also Fernando added the link to the YouTube channel where we post the recordings about a week, 4 or 5 business days later. So the next webinars we have, the next one is in a couple weeks on Wednesday, July 22nd or 21st at the same time, 3 p.m. Eastern Standard Time. We'll have Dr. Susan Sigward, Director of USC's Human Performance Laboratory. Her research focuses on the identification and amelioration of impaired mechanics as they relate to lower extremity injuries with a focus on knee injuries. Please join us for that one. It's going to be great. And then on Wednesday, August 11th, at 3 p.m. Eastern Standard Time, we have to have Dr. Charlie Shearer. He'll be presenting on visual processing speed, how quickly the mind can perceive what the eye sees. So we'll have more specific titles for you there on the website and hope you can join us for those. And I believe that's all. Thank you so much, Dr. Berme, for your presentation. And thanks, Dr. Santos, as always. And we hope to see you all soon. Stay safe and healthy.
Thank you.
Thank you. Thank you all.
Bye-bye.
Bye.